We're going to continue working with hypothesis testing. In this particular case, we're going to start to talk about the concept of the p-value. So keep in mind that this, right for now, is in the context of our large sample hypothesis testing of means. So we're doing hypothesis testing with means, we're doing large samples for right now, and so we have sample sizes greater than 30. Now, up until now, we've been doing everything in terms of rejection regions. All right, and that's basically where the level of significance alpha, whether it's left tail, right tail, or two tail, you have to set it all up. But essentially, you create these boundaries. And these are rigid boundaries that you can then look at, calculate your test statistic from your data, see where it falls, and depending on where it falls, you can tell if you have rejected the null hypothesis or if you fail to reject it. All right, well, every once in a while when I do teaching, I get around to a topic that I get really excited about because p-values in this case is something that gives a lot of students a lot of heartburn, a lot of scratching your head and trying to figure out what it really means. Well, I'm excited because I can explain this to you, I think, with some concrete examples, and especially after we get through this, we do a couple more examples. Hopefully, I believe that you will have a very, very good understanding of what p-values are intuitively. Number one thing before we do any kind of diving into this is I want you to keep in the back of your mind that the purpose of a p-value, really the process and sort of the reason that we do it is really no different than what we've been doing before. Essentially, we want to figure out when we can reject that null hypothesis and when we fail to reject it. So before we were using the rejection regions and figuring out where it falls. Here we're doing something very similar. At first it's going to look totally different, but then when I start talking about it enough, you'll realize it's exactly the same thing. So keep that in the back of your mind. We're using it for the same purpose. So let me just go down my list and make sure I say everything. Rejection regions work perfectly fine in statistics. There's nothing wrong with rejection regions. But p-values are more common to real research. So if you read a real research paper in statistics, they do a big study, they figure out what the hypothesis is and reject the null hypothesis, you're going to see p-values running around their explanation. So it's much, much more common. I'll explain why it's more common in real research. And so that's why we learn it here. And I've already said this once, I'll repeat it again. P-values are just another trigger to decide when we should reject that null hypothesis and when we should fail to reject it. First, I need to write down a book definition of what you're going to see in a book, what a p-value is. So let me get that down for you. But just keep in mind, don't worry too much about the definition as we write it down. I mean, I'll kind of explain it, but as we go through it, you'll get a much more intuitive understanding of what a p-value is that will be much more concrete than what I'm going to write down here. The following is what you'll typically see in a book. It'll say p-value, and a book will typically define it as follows. And this is a good definition. There's nothing wrong with it. It's just I need to show you some pictures for you to really understand it. It's basically the probability, and by the way, that's called a p-value because it's basically p for probability, of obtaining a sample. I'm going to put in quotes here because I need to explain it. More extreme than the ones observed in your data, assuming that the null hypothesis is true. The crucial part of what we're reading here is that the concept of a p-value is just a probability. And you know what probability is. We've been talking about that for ages in this class. Probability, right? It's a decimal between 0 and 1. It's a probability of obtaining a sample more extreme than the ones observed in your data. Now, what do I mean by observed in your data? It's because all of these hypothesis tests involve, you write down your null hypothesis, you write down your alternate, and then you go get some data because you need to try to, disprove the null hypothesis or reject it or whatever. So you go ask 23 or 28 or 99 people what they had for breakfast that morning or whatever. That's the data. So you collect that data, that sample data that you have, whether it's 50 samples or 60 samples, that's your sample data. And you have all of those different values there. Typically, you're looking at a mean. In this case, we've been talking about hypothesis testing of means. So you're looking at the length of pencils on an assembly line, volume of water being filled into, the bottles of water in a factory or something. You're talking about numbers, and the hypothesis tests that we've been doing so far have been all about the mean values of those things. So we go and select some to study and sample to try to test that alternate research hypothesis, and we get the values back. The p-value is the probability of obtaining a sample more extreme than the ones observed in your data. So you have a collection of data that you get from the assembly line or whatever, the 25 samples or the 50 samples that you have. That's the data that I've collected. The p-value is giving a representation of what would be the likelihood of getting a data even more extreme than the ones that I actually did collect. And the reason I put more extreme in quotations here is because it kind of depends on the problem that you're doing as to which way is what more extreme actually means. In other words, if I'm doing a right tail test, right tail will be that way, then basically I'm measuring the length of pencils, and I think my research hypothesis is that the pencils are greater than 3 meters long. Right? So my data more extreme is going to be in the right-hand direction, more extreme towards that tail. But if I'm doing a left tail test, then more extreme means more direct, more extreme in the left-hand direction. I think a lot of this can be simplified by writing some of this down. So let's say that I have a left tail test, right? Very common thing that we do in statistics, left tail test. So let's draw a picture of it real quick. So what we have is a little distribution like this. This is a z distribution or a normal distribution centered at 0, okay? So what it's basically saying is if I'm doing a left tail test, don't forget what I'm really doing. Let me switch over to red here. On the left tail test, there's always a little region here off to the left, right, that we shade. Right? Now, typically in previous problems, this shaded region has always been the level of significance, right? That's what I always told you. Your level of significance goes in your tail, and then your test statistic just lands wherever it lands, and you draw your conclusion. Here we're doing things a little bit different. I'm just explaining what a p-value is to you. If you're doing a left tail test, then by definition the null hypothesis is here, and we suspect that the candy bars, in this case if it's a left tail test, are shorter than they should be. In other words, we think they're getting smaller than the null hypothesis says, so we're moving this way. Okay. Now, when we do the sampling and we get all the values of the candy bars, we calculate a test statistic. That's this number, right? That's what we've always been testing based on the sample mean, hypothesis mean, and the standard deviation of the samples and the number of samples. We get a test statistic here. So I'm going to put that z down here. This is what we get from our sample data. This value of z comes from the sample data. Right? So it's kind of a representative, this value of z is kind of like a representative indication of what the sample data really is telling you. It's taking into account the mean, the standard deviation, the number of samples. So that's what this kind of means. This whole time we've been comparing this number to the level of significance, basically, and where that falls on the chart to figure out if we reject the null hypothesis or not. So forget about rejecting anything. Forget about testing it right now. The concept of a p-value is basically this value of z comes from the test statistic. It is the test statistic, and it represents your sample data. So when we say the p-value is the probability of obtaining a sample more extreme than the ones observed in your data, what I'm basically saying is that this value of z is called the test statistic, and this comes from my sample data. So all of these values here to the left, all of the z values to the left, these are more extreme. All of these possible values of z to the left are more extreme than this one. And the reason I'm counting to the left as being more extreme is because this is a left tail test. All right. So the bottom line is the p-value is, well, geez, let me switch over to green. The p-value is this area that's shaded right here, right? It is the probability. Remember, probabilities are areas under a curve of obtaining a sample more extreme than the ones observed in your data. My data gives me a sample standard deviation, a sample mean, a sample standard deviation, and the number of samples. Here's what we're relating to the hypothesis, the null hypothesis. We get a z value back. This represents my set of data. I'm saying that it falls right here. I'm not doing any testing yet. I'm not testing any null hypothesis. I'm not doing anything like that. I'm just saying the data that I get back is kind of represented in the chart here. It's far enough, it's sufficiently far from the null hypothesis to the left. We're doing a left tail test. There you go. Data points more extreme than the ones that I've actually collected are by definition to the left. And the area of all of those possible data points that I could get to the left is what we call the p-value. right? More extreme means to the left in this case. Now let me go over here and we'll do now a right tail test. And hopefully you kind of have an idea of what it's going to be before we actually do it. But let me go ahead and do it just to be absolutely explicit. In a right tail test, we have a distribution, same as we do before, which is always, by the way, centered at 0. Remember that. And these are normal distributions because we have large sample sizes, right? So I collect my data. Let's say I'm doing a right tail test and I have, candy bars coming off an assembly line. My research hypothesis says these candy bars are longer than 10 centimeters. That's the research, the alternate hypothesis, so longer than 10 centimeters. That would be a right-hand symbol. So I would be doing a right-hand, right tail test. Okay, so I would collect all that. I would go and look at 35 candy bars off the assembly line, and I would get information from that. I would get a sample mean. I would get a sample standard deviation, and I know how many samples that I collected. This is the hypothesis mean, the null hypothesis mean. I would calculate this number, and I would get a value of z. This value of z is kind of a representative, it's like one number that generally represents the entire set of data that I collected. It's one number, right? So this value of z goes here, all right? And what I'm basically saying is that all of these values to the right are more extreme than my data. Right? And a p-value is the probability of obtaining a sample more extreme than the ones observed in your data set. So my data set returns a value of z here. Everything to the right we're saying is more extreme because it's a right-tailed test, right? And the probability of getting something more extreme than my data set that I had here is what we call the p-value. So it's literally the area under the curve to the right of the test statistic z that you calculate for your data. In this case, over here, it's the area to the left of the test statistic that we calculate for our data. So I know because I'm using red shading, and I know because I'm shading the tails, some of you guys are thinking that this is the level of significance. It's not the level of significance. All I've said is that I calculate the test statistic from my sample data. It's representative of the data that I have measured. I put it on this guy, and then more extreme to the right for a right tail test is called a p-value, so it's the area to the right. More extreme to the left is going to be, in that case, for a left tail test. That's why I put more extreme in quotations. Now there's one more case I want to show you, or in fact, actually, before we get to that, let me go ahead and give a little bit more concrete examples of left and right tail testing. Okay, let's say, as an actual example, that the null hypothesis is that the mean is greater than or equal to 0.15, and the alternate hypothesis is that the mean is less than 0.15. So this is a typical problem that you could actually have. The alternate hypothesis is to the left, so you know you're doing a left tail test. That tells you that. All right. Also given to you in the problem, you're given that from the data, the test statistic z is negative 1.34. This doesn't fall out of thin air. What this basically is you collect all of the lengths or the volumes or whatever it is you're measuring, and you dump that information, the sample mean, the sample standard deviation, and the number of samples, you stick it into the test statistic, and out comes a value of z. That number of z, that value of z is representative of the data set that you have. It kind of takes into account all the data points, the spread of the data and everything, and out comes one number that's kind of representative of that whole data set. That's what we've been using it for all along. We've been using that one representative number to tell us if we're in the rejection region or not. Okay, so that is all given to us. We haven't done anything yet, but we know we're doing a left tail test. So if I were to draw this, I would draw something like this, and I know that I'm doing a left tail test. Okay, so the bottom line is the value of z that comes about from the sample data, negative 1.34. And since I'm doing a left tail test, I come up here and I shade this guy to the left because I'm getting the probability of getting a sample more extreme than the data that I actually collected. So this area here is called the p-value. All right, now how do we actually find the p-value? We haven't actually calculated anything yet. How do we actually find it? Well, this is a normal distribution. You have a chart of a normal distribution in the back of your textbook. Every statistics textbook does. Don't forget, the normal distribution gives you the area to the left. It's different than the t-distribution, which gives you the area to the right. I know it gets a little bit confusing. You always have to remember that the table for a normal distribution is giving you the area to the left. So what do we do if we want to find this p-value? Well, we have the value of z, and it has the area shaded to the left of z, so all we literally have to do is go to the table, right, and find the probability that z is less than negative 1.34. So literally all we do is look up z negative 1.34 in our z distribution table. The area that it gives us is the area to the left, which is exactly what we want. And I get 0.0901. So that means the p-value 0.0901. That is the p-value for this problem. So if you were given a situation where somebody says, here's the null hypothesis, here's the alternate hypothesis, here's the z score that comes from the sample data, calculate the p-value for this problem. Now notice we haven't done any hypothesis testing yet. I haven't even gotten to that yet, but I'm just wanting you to get practice with finding the p-value. Well, the only reason you need this is to know that it's a left-tail test. This is representative of our sample data, so we plop it on the chart, and since it's a left-tail test, the probability of getting a value more extreme than our sample data would be the probability of to the left of this value of z, which I can readily look up in the back of any book. So that's how you find a p-value for a left-tail test. Right? Now, what happens if we have a right-tail test? Okay, what happens if we have a right-tail test? Well, for a right-tail test, for a right-tail test, let's pretend that we have a null hypothesis, which has a mean of less than or equal to 0.43, and an alternate hypothesis, whoops, I'm going to put an A there, a mean greater than 0.43. And let's say from the data, z is equal to 2.78. So all we have is this, and the question is, what is the p-value for this problem? Notice we don't have a hypothesis. We have some hypothesis on the board, but we haven't been asked to test it. We haven't really been given a level of significance. We haven't really been told exactly everything about the problem. All I want you to do for this problem is find out what is the p-value. Well, you have to know what a p-value is. It's the probability of getting a value more extreme than the sample data that you collected. Now, we don't have the raw data, but we have the z-value, the test statistic that came from that guy there. So let's go ahead and draw a picture and get our bearings for what we actually have and what we actually need. So here's our distribution. This is a z or a normal distribution. And notice that this is a right-tailed test. This is a right-tailed test. So 0 goes in the center, and this value of z that I got from my data was 2.78. Right, that is a representative number in terms of z that kind of represents the whole data set that I've collected. We put it on the curve right there. What would be the probability of getting a value of next time we select a sample or whatever, of being more extreme than that? Well, this is a normal distribution, so we go up here and we shade to the right. More extreme in this case means to the right because it's a right-tailed test. More extreme in the previous case was to the left, because it's a left-tailed test. So the phrase more extreme really depends on the kind of problem that you're dealing with. That's why I put it in quotation marks. So what I'm looking for is the probability that I select my next sample and I get a value more extreme than the data set that I'd previously collected. So that means that this area here is going to be the p-value, the area under the curve to the right of this value of z. So in order to do that, you can use your normal distribution table in the back of your book. The probability of getting a value of z greater than 2.78 is what I'm after. But remember that when you're using a normal distribution, you can't just put the number 2.78 in there and circle the answer, because what we're looking for is the area to the right, right? But if I actually put 2.78 into the normal distribution, it's going to give me the area to the left. In other words, it's going to return the area of everything over here. So if you remember back to the very beginning of mastering statistics, like the very first volume when we started talking about the normal distribution, we basically said when you're using that table, if you want the area to the right, the way you actually handle it is you basically say that's going to be equal to the probability of z, you flip the sign around, negative 2.78. Because remember, everything's symmetrical. This is 2.78 here. I'm interested in this area. The area is the only thing I care about. If I look on this side, right around here, z is negative 2.78. And the area to the left of that negative value of z is going to be exactly the same as the area that I care about here. So when I'm trying to find areas to the right with a normal distribution, I flip the sign around, the inequality around, and I change the sign of z there. So I go into my chart and I look up the value of negative 2.78 in my chart, which is somewhere over here. It's going to return an area to the left. That area is the same as what I care about. So whenever I do that, I'm going to get 0.0027. So all you have to do is say that that is the p-value. 0.0027. That's the p-value. The p-value literally is the probability of obtaining a value, like the next sample I were to take, the probability of obtaining a value more extreme than the data set that I've collected. The data set that I've collected is represented mathematically by this test statistic. It contains kind of all the raw information. It boils it down to a value of z. So that's what a p-value is. I keep saying it over and over again. I want you to visualize that the p-value is an area to the right, or it's an area to the left. And when we get into situations where it's a two-tailed test, it's going to be very similar, and I'll get to that whenever I get to that. But for right now, I want you to understand the concept of a p-value. Notice we haven't done any actual hypothesis testing yet. I haven't even told you how to use p-values to make decisions, right? But I told you at the beginning that the big overall arching concept here is that p-values are going to be used to tell us if we reject or fail to reject a null hypothesis, just like the rejection regions we did before. I promise you that we are going to get there. You are going to understand, but you have to take it kind of baby steps with me. First, understand what a p-value is. It is the area to the right of the value of z that you get from your test, that you get from your sample data if it's a right-tailed test, or to the left if it's a left-tailed test. All right, make sure you understand that. So we've done two problems where we've calculated the p-value, one for a right, one for a left. I want to stop here, go on to the next section where I'm going to show you how to use what these p-values are in order to make decisions. And in other words, to tell us if we reject or fail to reject a hypothesis. Learn anything at mathandscience.com.